So what I will do is just make a brief recap of what we said last time. So we started from so we started from structural glasses. And in particular, we considered R spheres. We discussed the phenomenology of the glass transition. And then we jump to the infinite dimensional solution, and we discussed all the transitions that appear there. Okay. Then we went to constraint satisfaction problems. And in particular, we discussed the random coloring problem. And then we underlined that actually there is a deep connection between these two, in the sense that there is a set of phase transitions that appear and that are basically of the same nature. Okay. And so the most important point is that these phase transitions involve kind of ergodicity breaking, in the sense that the space of solutions of the constraint satisfaction problems or the phase space in the context of structural glasses gets clustered. Okay. And then starting from that, we introduced a model. That is the spherical random perceptron. Okay, so let me remind what was the model. It doesn't go up. Okay, I can write. Okay. Okay, so this is a model that has both features of constraint satisfaction problems and structural glasses. So it has a model for a set of continuous variables. So I will call X the set of variables. And these variables satisfy, so they live in on an n-dimensional sphere, in the sense that they satisfy the spherical constraint. So the sum from 1 to n of xi squared is equal to n. Okay. So these are the variables that we want to find in the constraint satisfaction setting. And then we introduced a set of random vectors, xi mu. So these are n-dimensional vectors. And each component is a random variable that is distributed according to a Gaussian distribution with zero mean and unit variance. Okay. So the factor graph of this model is simple. It's a fully connected factor graph. Okay, so each variable xi enters in all constraints, and each constraint can be written in this way. So I define a gap variable, h mu, that is just 1 over square root of n xi mu dot x minus sigma. Okay. So the control parameters of the model are sigma, this one, and the number of random vectors. So mu goes from 1 to m, and m is equal to alpha times n. So the number of random vectors scales with the system size. Okay. So what you can do now is to define, so the CSP, the constraint satisfaction problem, is find x such that h mu is greater than 0 for all mu. Okay. So you can define an Hamiltonian. So I define it in this way. And V so this is a kind of energy, and it's positive whenever a constraint is violated. Okay, so if h mu is negative, then you pay a little bit of energy, and the amount of energy that you pay is proportional to the square of the gap. Okay. So from now on, I will closely follow two papers. So I just give you two references. So as I told you last time, this model was introduced by so it was introduced a long time ago, but in the context of constraint satisfaction problems and for the relation with the geometry transition, it was studied a lot by at the beginning by Franz and Parisi. And the reference is J. Fizet. So 49. It's a paper of last year. And then the details that I will try to discuss in these lectures can be found in this paper. Oops. It's a paper that appeared in ShePost. 2.0, and it's up this year. Okay. So the idea, in order to understand and the space of solutions of this constraint satisfaction problem, what you can do is to define a partition function. So you have an energy, and you can define a partition function. Okay, and here I indicate with this the flat measure over the n-dimensional sphere. So I'm just integrating over all the vector x such that the spherical constraint is satisfied. And here beta is the inverse temperature. So why I want to introduce this partition function? So the idea is that by computing this, and in particular the log of this partition function, you can have access to the space of solution. This is an idea that dates back to Gardner and Derrida. Okay, so in particular, if you are in the SAT phase, so where you can find solutions, taking the zero temperature limit just gives you the number of solutions of the problem. Okay, because if I take the zero temperature limit, then this is either 0 if x is not a solution, or it's 1 if it is a solution. And so I'm just counting the volume of solution. So this is in the SAT phase. In the unsat phase, instead, where there is no solution to the constraint satisfaction problem, taking the zero temperature limit allows me to compute the ground state of the problem. Okay. Okay. So this z, of course, depends on quench disorder. So I will indicate it like this. Because the Hamiltonian, of course, depends on quench disorder through the gap variables. Okay, so what we would like to do is to compute a phase diagram, where actually we have two parameters, sigma and alpha. And what we said last time is that we expect that for in this region, the problem is kind of simple. In the sense that the constraint satisfaction problem is convex. Instead, here, in this region, the problem can be hard. And the problem is non-convex. Okay.
Sorry, what is alpha?
Sorry? Alpha. Alpha is just the fraction of constraints. So you have mu, the number of constraints that goes from 1 to m, and m is alpha times n. Okay. Okay. So since we have the partition function, we can define the free energy. So let me. Okay. So this depends on the disorder because the partition function depends on the random vectors. But what we would like to compute is the average of this thing. And the reason is that we are interested in the typical behavior. Okay, so we would like to understand how a typical constraint satisfaction problem behaves, if it is SAT or it is unsat. So what we would like to compute is the average of this. I define. And now, since this is the free energy, you can expect that this is equal to the energy minus T times the entropy. So this is just basic thermodynamics. And now let me discuss a bit more the t going to 0 limit. So if you are in the SAT phase, then you know that the energy is 0, because you can find solutions to the constraint satisfaction problem. So the free energy is just minus t times the entropy, and the entropy is just the log of the number of solutions of the CSP. So if you take, in this case, if you just do minus 1 over t, sorry, then you get the entropy of solutions. He said if you are in the unsat phase, then the entropy goes to 0, and then you get just the ground state of the problem. Okay, so let me call it like this. So if you are able to compute the free energy, then you have access to three things. So one is the boundary between SAT and unsat. In the SAT phase, you get the entropy, yes, the entropy. And in the unsat phase, you get the ground state energy. Okay. So what we will do now is to compute this free energy. Okay. Okay, so what I will do now is to use the replica method. So this is extremely powerful, but it's also not rigorous. So it has a strong heuristic value. And what people now do typically is to use another method that is called the cavity method, through which you can prove mathematically what comes out from this method. Okay. So what is this this method? So what we can do, so you see the problem here. So we would like to compute the free energy, and this is the average of a logarithm. So how to compute this thing is very hard. So it's a complex problem. And the replica method just gives you a way to compute the average of the logarithm. So how? So what you do is the following. So what you can do is that you can replace this by the limit Okay, so let me rewrite it better. So it's trivial to see because this quantity is just e to the n, right? And then when you take the derivative with respect to n, you have just, so if you take the derivative, this is just and so when you take the n to 0 limit, this disappears and then you get back the log. Okay. So this is trivial. Okay. And now you can ask if this helps in some way. So in general, it doesn't help in the sense that it's hard to compute this average for generic values of n. And in particular, we are interested in the limit where n goes to 0. But if you forget for a moment that n should go to 0, what you can do is that if n is integer, then you can compute easily this thing. And the reason is that you can represent this power in this way. So in this case, this is just the product from A that goes from 1 to n okay. So if n is an integer, then I can rewrite this power in this way. Okay. And then I have to take the average over the disorder. So you see that when n is integer, then you get a system where you have n copies of the original one that are called replicas. So you have n replicas appearing. And so the strategy now is to compute this thing for integer n, and then try to get an analytic continuation in order to get this limit. So this can be done. Okay, so the first thing that we can do in order to compute this is to define this variable. And of course, since you have n replicas, you can define its replicated version. Okay. And now you can rewrite this in the following way. So remember that here, this h is a function of, so and h mu can be rewritten like r mu minus sigma. Okay. Then this is just E. This. And then what I do is that I insert okay. Sorry, this must be. Let me put it here. Okay. I just put a Dirac delta in order to say that this quantity is equal to that. Okay. And now I can use a Fourier representation for the Dirac delta. And I get. So of course this must be averaged over the disorder. I want to average over the size. And so this gives okay. I don't know, maybe, can you see? Okay, maybe I can rewrite it here.
I'll send you that. You can just put it up.
So, okay, yes. So I just expanded this Dirac delta using the Fourier representation. So you have a hair hat variable for each R. Okay. And this, of course, must be averaged over the disorder. Okay, so okay. So now you see here. So this thing doesn't depend on psi.
Pierfrancesco, I do not understand why you integrate over R, A.
This one? Because I just want to enforce this. If I integrate over R,
R at you enforce this.
no. Here I need to integrate over R because I want that here this thing appears, right? So if I integrate over R, instead of having this, I get this, right? And then I have to represent this, okay? Okay, so here the disorder appears only in this term, okay? And so what we can compute is just the average of that. So in the end, what we need to compute is just the average of this term here. So it's the average of e to the minus e. So the sum over a comes from this product, of course. I can put the product here, and it just gives me a sum. Okay, and so this is given. So you can integrate over all the components of the random vectors. So it's just a Gaussian integral. And what it gives, it's just the exponential. So maybe I can try to do it. It's fast. So this is just So this I should not be confused with this I, of course. So this is the imaginary unit. I just expanded this scalar product, and this just gives it's just, sorry, I forgot square root of n. It is just the square of this times that. Okay, so the square of this gives me the minus sign, and then here I have to sorry. So here there is a factor n that comes from the square of this. Okay. And then this can be rewritten easily this way. Okay, so I just expanded this square. Okay, so let me just rewrite it in a better way. Just a simple thing. So it's minus 1/2, and then I have a sum over mu then I put this sum here, okay, and then I write 1 over n okay. So the nice thing, the interesting thing, let's say, of this expression is the following. So we started from this expression here. So here what you can see is that all replicas, they are non-interacting in the sense that there is no direct coupling between them. Okay. So once you average over the disorder, then so this average generates interaction between different replicas. Okay, so we started from a system of non-interacting replicas, and then we get a term that involves some interaction between them. So this is the first comment. The second comment is that there is this quantity here that appears quite naturally, and this is called the overlap. So QAA is equal to 1, and the main reason is that this is just the spherical constraint, right? So if A is equal to B, then I just get the sum over IA squared, and I know that this is equal to n, because the variables are spherical. And then if I take Q A different from B, this is just a measure of similarity between the vector A and the vector B. It is just the scalar product between them. So if Q A different from B is close to 1, it means that the two vectors are very close one to the other, are almost parallel. Instead, if Q AB is going to 0, then this means that the two vectors are orthogonal. Okay. So let's come back to the free energy. So I rewrite it in this way. So the independent elements of this matrix are just the ones for A different from B, and in particular for A less than B, just because this is a symmetric matrix, right? So I rewrite this in the following way. I'm just rewriting the expression for this average. And then I have okay. And then I have minus 1/2. So it's just the result of the integration over the noise. Okay, so I just wrote this. Okay, so let me write this way. And then here I put a delta. Okay. So now what I can do is just that I add here I include the delta of QAA just to enforce the spherical constraint. And then here I've just put a free integral over the r-dimensional space. Okay, is it clear? I just put I just included a Dirac delta in order to enforce the spherical constraint.
So you have to put also the equal and the integral over the Q.
Yes. No, I don't want to put this. Okay. I fix QAA. This is not a variable. This is just one. Okay? Okay. So now you see that the only thing that depends on x is just this factor, right? And so the integral over x is simple. So I compute the integral over x of this quantity. So let me define it. This is a function of q. It's a Jacobian. And it's just so the way in which I compute this is just I introduce the Fourier representation of this function. Okay. Sorry. Let me just, before doing this, let me just multiply everything by a factor of n. So here I have and here I rewrite okay. So I will always forget all the constants that appear here because they are irrelevant at the end. And now you see that the integral over x becomes Gaussian. Okay. And so this is proportional to so and now here I write a matrix Q tilde, and Q tilde is just let me write it like this. Okay, so I just introduced Q tilde because in this way this term becomes okay. And now you see that when you have this then for each component of the vector, you have a Gaussian integral with Q tilde as a kernel. And therefore, the result is just the log of the determinant of Q tilde. And then you have n times this factor because you have an n-dimensional space here. Is it clear? Do you want that I do it more carefully? It's okay? Okay. Okay. So now you have this. And now suppose that you take n very large, then you can use saddle point method. Okay. This term here can be rewritten as okay. And then if you use saddle point method, you just take the variational equation with respect to Q hat that enters inside Q tilde. And then the saddle point equation is simple because it just tells you that Q, okay, so this is saddle point. Okay. And then if you plug this inside this function, then this just gives you a constant that I will forget. And therefore, J of Q is just proportional to the exponential okay. Okay, so this way of performing this computation is a kind of classic way to perform the computation. There is another one that I didn't do, but if you are curious, it's contained in the appendix of this paper. And this is a physical chemistry paper. And it's 2013. This is just for curiosity. Okay, so now we have the Jacobian.
Excuse me.
Yes?
Could you just explain? I don't see why Q is Q tilde minus 1. Is it obvious?
You just take the saddle point.
But you have to take the derivative also of the log that?
Yes, so this just gives you Q tilde minus 1.
Okay.
The derivative of log that gives you Q tilde minus 1. Okay.
The sum there is Q tilde, Q hat. The sum just above.
This one?
The sum above.
Yes.
The Q hat.
No, this is Q.
Q?
Q tilde as Q hat. Okay.
Ah.
So a simple way to see this is just sorry?
The comatrix?
Yes.
Okay.
So if you just do it for a matrix of one times one matrix, then it's 3.
Okay.
But then, I mean,
I'll try to
it's
find
consistent. Okay, so okay, so
Also, you have your QAA equal to 1.
yes,
But still you do integration over all QAB for A less or equal to B.
Yes.
But then you write n to the power m minus 1, so somehow you do integration over, it seems like capital N, it seems like still for A less than B, so it was.
No, it's still, you said the factor n,
Yeah.
okay, maybe it's plus 1, so you have to include the diagonal.
Okay. That's what I
Yeah.
would presume of you.
No, wait.
If
No, it's just minus 1. Because so you have,
Yes, but
yeah,
so you
no,
have
you're right,
integral.
yes. But okay, this is,
No, the details. Yes,
okay. Okay, so then so this is proportional to, so I don't write the constant. And then here again I have okay. So now you see that so the integral over these variables is decoupled in the index mu, right? So here you have a sum over mu, a sum over mu, and a sum over mu. Then just this term can be rewritten as sorry. Hup. Right? And therefore I can put this inside this exponential. So you can write it, let's write it this way. And then this S of Q then you have M, this M, that just gives you a factor alpha, because you rewrite this as, this term here as log of this integral, and then you divide by n, multiply by n, and this is alpha. Okay. And this n here is just this one. And so you have n times the log of, let's call it z. That is not this one, of course. And z is it's just this integral, okay? So, okay, I can rewrite. So this integral okay.
Can you explain why you could do this trick of replacing the sum of mu with the power n? Because you integrated the disorder before?
I have just, this is a kind of dummy variable. You see, it's an integration that is repeated n times. So you have the same integration to the power m.
Just in the steps before, you couldn't do it because you didn't have such a factorized expression.
No, I would say no. Okay. Okay, so okay, now let me focus on this quantity. So I always use the same index, of course, but this one is, I mean, when I put the parentheses, this means that the product is close, right? So I can use the same index. So now what I do is I transform this integral, that is a Gaussian integral over, actually it's not Gaussian, but it has a Gaussian term. So I want to transform this Gaussian term in a differential operator. And the trick is, it's very easy. So you just rewrite this as so oops. And here I just write minus e So you see that whenever these derivatives act, I just take down a factor e minus e times r. Okay, and so if you expand this in the power series, then you get the power series of this term, right? And now this is interesting because you can integrate over these at variables. So the integral here just gives you a set of Dirac deltas. Sorry, here I forgot. See? Okay. Okay, and now I can just do the integration over R. Okay, so I just replace this by HC. Can I do it? I just replace this by HC. Okay. And then here I write a product. So sorry, here I forgot. Of course, you have to take h that is equal to 0, right? Because otherwise you have this term that is still there. You always have to take h equal to 0. Okay, so we will see that this is very useful. Oops. So I just substitute the function here. So this is just the x and then here I compute everything in minus sigma, right? It's just the same thing. Okay, so we have this, we have the integral over q, and then we have exponential of n times f of q, and s of q as this expression. Okay, just before the break. So remember where we started. So we wanted to compute the free energy. And then we said, okay, this is minus limit okay, so I already used the saddle point. So what I want to do now is just to exchange these two limits, which is something that it's not rigorous, right? So in principle we cannot exchange them, but let's do it. Okay? And now if I do it, I can use the saddle point method to estimate this integral. Okay? Because I have an n factor here. And then I can try to compute this derivative. Okay? So maybe we can make a break now. And then... Okay, so the idea now is that we compute this integral with saddle point. And so we take the saddle point equation over Q. So we have ds and this is for A that is less than B, right? Because we say that QAA is equal to 1 and it's fixed. So if you take this at the point, then you have again the derivative of the log of the depth, that is Q minus 1. Do you want that I show you that the derivative of the log of the depth is Q minus 1? Or is it's okay? Okay, so I give it for granted and maybe I can write it in the notes, the derivation. So you have Q minus 1 equal to minus alpha. And then I take the derivative with respect to Q and B. So you have two terms, one with A less than B and then the other one with A greater than B. And they are the same. So there is a 1 over 2 factor here. And so what you get is just and then when I take the derivative, I have this differential operator that appears here. And so what I have and then here you have exactly the same thing with this factor that goes to 1, right? I just write it like this. It's exactly the same thing where I replace this with 1. Okay? And so this is an equation for A less than B. Yes?
On the left you have A and B which is fixed, and on the right you sum over them. Do you need to change the indices?
Yeah, sorry. You're right. You're right. Sorry. Okay. Can I use C here? It's not the same C here. Let's call it E.
On the left, maybe.
Okay. Thanks. Okay. So this is an equation, but it's very complicated because in principle you want to find a solution for Q. So you want to find a solution for Q. And then in principle there is a second problem that you want to find an analytic continuation . When n goes to 0. So you want to find a family of solutions and then take the limit where n goes to 0. So this is very hard in principle. So unless in general the saddle point equations are like this. So it's not clear if there is a structure with which you can solve at given n for all the matrix elements of Q, and then take n to 0. So one thing that one could try to do is to compute this with a given ansatz that is easy enough to take the analytic continuation. Okay. So before doing this, what I would like to do is to try to clarify what is the physical meaning of Q. Okay. So let's stop for the moment here. So up to here, the problem is very general. And then we will try to do ansatz on the form of the matrix Q in order to get saddle point equations. But before doing that, let me try to clarify what is the physical meaning of Q. So So let me do the following thing. Suppose that I consider two systems that are described by two variables, x1 and x2, okay, as before. And now these two variables have exactly the same quench disorder, okay? Now, what I would like to understand is what is the probability distribution of the overlap between the two. Okay, so Q12, again I define it this way. And then I would like to understand what is the probability distribution of Q12. So I write it and then I explain it. So this depends on psi, of course. The Hamiltonian depends on the disorder. So I have the normalization. So I have two normalization factors. And then here I put a delta. So of course, this probability distribution depends on psi. Okay. So if I extract from the Boltzmann measure two configurations, x1 and x2, this is just the probability to observe an overlap Q between them. Okay. And this depends on the disorder. So we would like to have typical quantities. So what we can do is to average this over psi. Okay. How do you do that? So you have this normalization factor here, and this can be rewritten as so I put a small n here, minus 2, and then I take the limit of n going to 0. Again. And now since I have this, again I can compute this quantity, you see, for integer values of n. If I'm able to do that, as we have seen we can do it, then I can try to compute this limit. So I can redo exactly the same steps that I've done before in order to compute this, this average. And so what I get is the following. So you see that you have n minus 2 copies here, and then you have additional 2 here, right? Is it clear? And so in the end I have n, small n replicas, right? And so I can redo exactly the same steps. And so what I get, averaging over the disorder, introducing the overlap, with exactly the same S of Q as before. Sorry, not the one over. Right? And then so of course this function is replica symmetric in the sense that it doesn't matter if I take here 1, 2, or 3, 4. Okay, I can take whatever I want. And so I can rewrite this as and then here I can write, let me see. Okay. So I just said, okay, the replica 1 and replica 2 have exactly the same values as generic replicas, right? So this way I get that. Oops. Let me write it. Where? Okay. Let me write it here. So the P of Q so you see that, okay. So when I have to compute this integral, I use again saddle point. Okay. So inside this delta, I have to put the saddle point value of Q, right? And so if I do that, I just get 2 over n let me call Q star the saddle point value. Okay, so the saddle point that I get from this. And so you see that if I'm able to compute the saddle point, I have access to the distribution of the overlap between two configurations of the system. So in particular, if I take the t to 0 limit, and I am in the sat phase, in the satisfiable phase, then two configurations are two solutions of the system. Okay, and therefore this just gives me the typical distance between two typical solutions of the constraint satisfaction problem. Is it clear?
Why don't you have the entropy of the saddle point?
Sorry?
The S of Q star.
Because this is of order n, small n. This is of the order of small n. Okay? Okay, so that's what I wanted to show. And now let's go back to the real problem, how to find the saddle point solution for Q. Okay, so Okay, so as I told you, finding the saddle point solution is a hard problem. So what we will try to do is to make some ansatz on the form of the overlap matrix, and then we will try to see if these ansatz are correct or not. So the first ansatz that we can try to do is the replica symmetric one. So we say that the matrix QAB, of course, it is equal to 1 if A is equal to B, and this is the spherical constraint. And then we say that when A is different from B, we always have Q. Okay, so this matrix, you can represent it in this way. So here you have 1 on the diagonal, and outside the diagonal you have Q. Okay? So now the strategy is the following. First, we compute S of Q on these ansatz. Okay? And then we find the saddle point over small q. Okay? Okay, so let's go back to S of Q. So S of Q is 1/2 log that of Q plus so H equal to minus sigma. Okay, so let's compute this first term. Okay, so what you can show, I will not do it, but you can try. If you don't manage, I can help you. So the det of Q, when Q is of this form, it's just given by 1 minus Q to the power n times 1 plus n minus 1 times Q. Okay, so we will, I hope that I will try to derive this result in a more general setting, but if you want, you can try to derive it by your own. Okay, so this is simple. So therefore, so remember that we are interested in the end we want to take, so at the end we want to take the derivative over n, small n, of e times n times f of q. And then we want to send n to 0. So what we are really interested in is the small n behavior of this quantity. Okay. So for n very small, then you can show that log of that of q divided by n, it's just 1/2 Okay, so let me rewrite it this way. So log of that is, sorry, 1/2 Okay, so this is easy. And now we would like to compute this one. Okay, so let me focus on the argument of the exponential function. So if I plug these ansatz inside this, what I get is simple, is Q alpha. Right? So the way in which you can see it is that this matrix can be written as 1 minus Q times the identity plus a matrix Q, so Q times a matrix that I call 1 tilde. And this 1 tilde is a matrix that is full of 1. Right? And therefore, when you plug this inside this expression, so when you have this, then you have just this term, right? And then when you take this, you have just this term. Okay, so now there is a small trick. It's nothing. And the trick is the following. So if you have something like that, terms of function, so this can be written in terms of a Gaussian integral. So it's just a convolution of a function f with a Gaussian. Okay, so I will denote it like this. This is a Gaussian with A here, convoluted with f. So the way in which you can obtain this is just by using, for example, perturbation theory. So you just expand this differential operator. Okay, I will do it. Okay, so this can be written as sum. Oops. Okay, so this is one. And now let me do it. Let me do this integral. So what I do is that I expand this function in a power series, assuming that we can do it. And so you have and then what you have then you have the decay derivative of h Okay? So this can be rewritten as sorry, here I so wait.
Oh, you heard already.
No, yes, sorry.
Yeah, this one, yeah.
Oops. And now, so this gives you something that is different from 0 only when k is a multiple of 2. And so you have just right? And then this, you just simplify these two. And then you have a to the k which should be this one. Okay. Okay. So let's use this. Okay. So we had so now what I do is I just use this trick for this part, okay? And so what I get is just e to the q over 2 and then, so you see that each a acts on a different term in this product. So you have just the product Is it okay? I just used the convolution thing on this part. Okay. So on this acting on that. Okay. So now you see here a very simple thing now, because suppose that I have a function. So this is a kind of very simple identity. So if I have of a function that depends on h1, so here I can put whatever power I want. And then I compute this on the same value, let's say h star. So all h equal to h star. then this is just sorry. Right? It's just the composition of. So I mean, do you see it? Is it okay? Do you want to explain more? So if you just do it for a function of, let's say, x1 and x2. So if I do so this is just, so let me do it the following way. If I do of a function, then this is just right? This is simple, right?
Yes.
Okay. And this is the same. Okay, so how do I use it? Well, you see that I have exactly the same structure. And so what I have is just that gamma. So let me rewrite it this way. So I have e to the q divided by 2. Then I have this term with all the same h to the power n. And then I compute h in minus sigma. Right? And then I use the same trick as before. So this is gamma of q. Sorry, this is 1 minus q. Okay? Okay, so now it's simple to take the n to 0 limit here. So remember that what we would like to take is to take the log of this and then multiply it by alpha. So we have that alpha. So I just rewrite everything. So we started from this. So this is alpha times log of this. So it's gamma of q. And now this is right. I just expanded for small n. And now, so this is small, so I can use the, so gamma of Q convoluted with 1 is just 1, because it's a Gaussian, it's the integral of a Gaussian. And so this just gives alpha n oops. Okay. So so therefore, so S of Q divided by n, it's just 1/2 Okay, so this is simple enough to take the variational equation with respect to Q. So if you take the saddle point with respect to Q, then you get the saddle point equation. I don't do the algebra, but it's easy. Okay, so this is the saddle point equation. And now you can solve it, for example, numerically. Okay, and now let me just make 2 comments. So this equation, you see that it's valid for every beta. Okay. And now what we would like to do is to take the 0 temperature limit. Okay. Okay, so let me do it. So now suppose that you are in the SAT phase. So if you are in the SAT phase, you expect that if you take 2 different configurations, in the 0 temperature limit, these are 2 solutions of the problem. Okay. And then as long as you are in the SAT phase, their overlap, that of course here is equal to small q, because this corresponds to 2 different replicas, will be smaller than 1, right? In principle. Okay. And moreover, e to the minus beta v of h in the 0 temperature limit, so for this just gives you the theta of h, right? because this is e to the minus beta h squared, sorry, theta of minus h. So you cannot have h, sorry, wait. So if h is negative, then you pay energy, then this gives you 0, right? So you want h to be positive, and that's why you get this theta. And so you can plug this inside this equation. And so you have q1 minus q. So this is from minus infinity to plus infinity. So here you have the convolution of a Gaussian with a function that is at theta. And you can compute it, and I call this function at theta and this function theta is just 1/2 1 plus the error function. So let me write like this, x. Okay? Okay, so you have a closed equation for the overlap Q.
May I
Yes, sir.
For instance, kind of Q is sort of product of these two
Yes.
square root of n of
Yes.
unit vectors, so it could be in principle negative.
Yeah.
Scalar product, and you have square root of Q, so somehow you seemingly assume that Q is positive.
Yes.
And is it obvious?
Well, yes, because what you want to do, I mean, in principle, the P of Q is symmetric. Okay? So you, okay?
Yeah.
So you just take Q, so you just solve it for Q that is positive. Okay? Okay, so once you have this, so suppose that you are in the SAT phase, and now you want to go towards the unsat phase. So what you can expect is that when you go towards the unsat phase, Q goes to 1. And the idea is that the space of solution is shrinking to just one configuration. Okay? And so when you have Q that goes to 1, this just gives you the satisfiability threshold. Okay? It's where the system, a typical constraint satisfaction problem becomes unsat. So what you do is that you take this limit, you plug it here, and then from that you get the satisfiability transition line. So, yes.
Last time, didn't you say that instead when you cross the border between SAT and unsat,
Yes.
you don't have the solutions go to 1?
This is for the coloring problem.
For the what?
For the coloring problem.
Ah,
In the random coloring problem where you have discrete variables,
okay.
then you have that when you cross the satisfiability threshold, the entropy of the space of solution is finite. So you have just islands of solutions that disappear. Instead here what is happening is that since you have continuous variables, these islands are shrinking to just one configuration, and then they disappear. And so in this case, Q goes to 1. Okay. So if you plug this limit there, then what you get. So the way in which you can do is just to use the, sorry, here I forgot, oops, hold on. So you can just use this asymptotic expansion. So for q going to 1. And then in this way, you get that the satisfiability threshold that I call alpha j, j stands for jamming, because here the satisfiability threshold is a kind of jamming transition. This is just given by okay. And so if you take back the phase diagram, so this is a line that does like that, and here is 2. So here, this, the system is sat. So this is the sat phase, and this is the unsat phase. Okay. So this line is just what you get from this. So next time what I would like to do is to consider this equation in the unsat phase, so here. And then I will compute this line coming from the unsat phase. So what we did here is to take the solution in the sat phase, and then we have taken the limit q to 1. And what I would like to do is to consider the other situation where I consider the solution in the unsat phase, and then I take the jamming limit that I will define. And I will obtain, of course, the same line. And then what I would like to do is to try to characterize a little bit this line. For example, I would like to compute what is the number of unsatisfied constraints when I cross this line. Okay. And so this I will do it next time. Okay.